Welcome back. So let's get to the big theorem that we've been building towards, the Chinese remainder theorem. What is it and how do we get to use it? Well, the Chinese remainder theorem says this: if the greatest common divisor of A and B is 1, hence they're relatively prime, then for any remainder A, mod A, and any remainder B, RB, mod B, there exists an integer n such that n is congruent to RA, mod A, and RB, mod B. If there are two such integers, n1 and n2, they are congruent mod A times B. By the way, it only lists this for two things. This continues for 3 as well. But I have 3 different remainders, different modulos. So how do we deal with this? Well, let me show you an example to kind of illustrate this. And then you will also work through some examples as part of your strategy this week. What is the smallest positive integer n such that n is congruent to 3 mod 11 and n is congruent to 7 mod 17? You can also write this as a system of linear incongruence. I just wrote this as a sentence, but it still works either way. Well, first and foremost, since the mod 11 and mod 17, 11 and 17 are relatively prime. Heck, they are prime, but they're relatively prime. That's the key thing. We can apply the Chinese remainder theorem. We can start by finding AB, which is 11 times 17, which is 187. We will save that for later. Now we need to solve the following 2 linear congruences. 17, so notice I took the opposite mod and I multiplied it, and I'm setting equal to 1. The reason is if I find out what y1 is and it's equal to 1, I can simply multiply this value by 3 and it will then end up equaling 3. So I'm cheating here and I'm essentially finding the inverse of 17 mod 11. All right, so let's go through and let's solve each one of these linear congruences. Let's start with the first one. Well, 17 times y1 mod 1, I'm sorry, congruent to 1 mod 11, is the same thing as 6, because 17 is congruent to 6 mod 11. 6 times y1 congruent to 1 mod 11. Okay, so we can actually set up a linear system where 6, that means 6 times y1 is equal to 11 times some number a plus 1. Or in other words, 6y1 minus 11a is equal to 1. Timeout. This is a Diophantine equation. How do we solve Diophantine equations? Hopefully you're saying Euclid's algorithm. All right. Here's the start of Euclid's algorithm. Pause the video, finish it. All right, so if you finished Euclid's algorithm, you end up with 6 times 5.1 plus 1. We can then work backwards. So 6 minus 5 times 1 is congruent to 1, or equal to 1, excuse me. But 5 is equal to 11 minus 6, so 11 minus 11 minus 6 is equal to 1. Or in other words, 2 times 6 minus 11 is equal to 1. Notice that gives us y1, which is 2. So because we solved this, whatever is being multiplied by 6 when we finish solving it is our y1. So guess how we're going to solve this equation? The exact same thing. So we start, now I can't make 11a smaller because it's smaller than 17 already. But I can set up the Diophantine equation, namely 11y2 minus 17b is equal to 1. And I can solve this using Euclid's algorithm. Again, go ahead and pause the video and use Euclid's algorithm. Now, if you did Euclid's algorithm, you probably noticed it looked a lot like the other one with one extra step. Because you start with 17 equals 11 times 1 plus 6. But the very next step and the very next step are identical to the previous Euclid's algorithm. Working backwards, again, we start with 6 minus 5 times 1. That's 6 minus 11 minus 6. 2 times 6 minus 11 is equal to 1. However, now we can replace it using this first equation. 6 is 17 minus 11. So therefore, 2 times 17 minus 11, or in other words, 2 times 17 minus 3 times 11 equals 1. Now, our instinct right here would probably be that it's -3. But remember, we want a positive value. So -3 is congruent to 14 mod 17. All right, so we have solved this, and in case you don't fully believe me, 11 times 14 is 154, which has a remainder of 1 when divided by 17. All right, so now we've solved our two systems. So let's put it together. And just to make it clear, here's our system. So the solution, I take this number from the first one, I take the other congruence, and I take y1. So this is y1 right here, because that was our solution. Then notice I take y2, multiply it by the opposite 11, multiply that by 7, because I have a 7, and I have this. Now, if I go through the process of multiplying this out, this comes out to be 1,180. Pretty big. However, now let's go back to A times B. As a reminder, that was 187. So 1180 mod 187 is 58. So because of all those things that we did to actually solve, here we are with our remainder. So n is 58. So let's, just to verify that this works, 58 is 11 times 5 plus 3. In other words, 3 mod 11. Similarly, 58 is equal to 17 times 3 plus 7, which is congruent to 7 mod 17. Thus, 58 is indeed our solution to this particular system. I hope that helps. Have a happy Thanksgiving. Let me know what questions you have.